Okay. Um, we have covered in chapter 2, we have covered resistors in series and parallel, right? Then we learned how to combine both those techniques together and reduce a large resistive network to one single resistance. Then we took it one step further by applying that same technique to a source. You reduce a large resistive network to a single resistance, apply Ohm's law, and then you're able to solve for the voltages and currents in the circuit, right? Now we will learn 3 techniques that can be applied to any circuit. Now, the series parallel equivalence technique that we learned assumes or presumes that the network of resistors is reducible. Oftentimes, there are some circuits networks comprised of resistors that you cannot reduce to a single resistance. And so this technique cannot be used for those kind of circuits. And so for those circuits, we use the techniques known as node voltage analysis and mesh current analysis. Now we will learn about those techniques, but before that, I want to talk about the third technique, which is superposition principle. And the reason for this is that the superposition principle is exactly the same as the series parallel equivalent analysis in certain ways, and it's a little bit of extension. Okay, so superposition principle analysis flows directly from the series parallel equivalent circuits. Okay, basically what it says is, now superposition principle is also it's not just electrical engineering. You can come across it in physics. It's a standard principle where it states if you have a circuit which has n number of sources, whether the source is a voltage source or a current source, the voltage or current at any given point in that circuit is a sum of all of those sources working together. Okay, so for instance, if you have a circuit which has, let's say, n is equal to 2 sources, let's say 2 voltage sources, okay, and you were trying to find, let's say, maybe voltage across one single resistor R1, then VR1 is a result of both these sources working at the same time. So when you perform your analysis, you can analyze the circuit with only one source active at a time. You find the resultant component voltages and add them up. Essentially, what you're doing is you're taking a circuit with multiple sources and you're breaking it down into separate pieces. And each piece is the entire resistive network with only one source working at a time. Then you analyze the circuit using the technique that we just learned, which is series parallel analysis. You find the voltages and currents present in the circuit. Then you move on to the second source. You again perform your analysis and you find all the voltages and currents present in the circuit. You take your set of data from the first analysis, set of data from the second one, you add them together, and you get your entire resulting voltages and currents. Does that make sense? Right? That in short is the superposition principle. So how do we analyze with only one source active at a time? Well, that's where I introduced the concept of reducing the source to zero. Now you say reducing the source to zero. Oftentimes it is simply referred to as turning off the source. Okay, turning off the source. Now, this turning off is a little bit different than the actual physical act of simply just powering it off. Okay. The concept comes from the fact that, well, let's take the voltage for instance. If you're measuring voltage between any 2 points, right, and you want to reduce that voltage to zero, what do we need to do? The only way that a voltage between any 2 points can be zero is if they're the exact same potential, meaning if there is a short circuit between those 2 points. If there is a short circuit between 2 points, let's call this point A and point B. If there's a short circuit between the 2 points, then the resulting voltage between these 2 points is 0 volts. And that's where the concept of reducing a source or a voltage source to 0 comes from. So if you want to reduce a voltage source to 0, you simply remove it from the circuit and replace it with a short circuit. Does that make sense? Again, this is just the explanation for how we do it. But more importantly, this is what you need to remember. Voltage source is replaced with a short circuit and current source is replaced with an open circuit. So this is an important concept. This is what you need to remember. I won't stress on the how of it. Okay. Then a current source. To reduce a current source to 0, meaning if you want to reduce the current from one point to another point in a circuit, if you want to completely reduce it to 0, the only way that can happen is if there is no pathway for the current to flow through. So you make the points or the pathway open. And so if there's no current flowing, I is equal to, put an arrow and 0 amps. And so for a current source, reducing a current source to 0 or turning off a current source means simply removing it from the circuit. You remove it from the circuit, and that would reduce it to 0. All right, questions? Any questions? Again, the important point you have to remember is this right here. Yes. Yeah, I'll show an example. Yeah. So now we take that concept, reducing a source to 0, and we split up our larger circuit with n sources into multiple different parts. Okay. So let's say we had a circuit with 3 sources. I'm just going to draw a random circuit. Voltage source, resistor, resistor, current source, let's just take 2. Actually, you know what? Put in one more over here. Now, it doesn't matter where the source is in the circuit. Okay. So you have a circuit with 3 sources, 2 voltage sources, and 1 current source. And we're asked to analyze this circuit using the superposition principle. So what are we going to do? We're going to split it into 3 parts. I'm going to call this VS1, IS1, and VS2. So I have 3 sources. I need to perform 3 analyses, once for each of these sources. So what I'm going to say is, if I have VS1 active, IS1 equal to 0, and VS2 is equal to 0. So VS1 is active, nothing changes there, everything remains the same. I reduce IS1, the current source, to 0. What does that mean? I leave it open. I leave it open. The circuit has now changed. and VS2 0, meaning replace it with a short circuit. Now all I am left with in the circuit is a bunch of resistors. And I can apply the series parallel equivalent analysis technique. I can reduce this large network of resistors to one. Reduce resistors to REQ. Does that make sense? Okay, so it's an extension of the previous technique. It's an extension of the previous technique. So even though there are multiple sources in a circuit, there is a way to analyze it by using the previous technique. And that is by breaking it up into different parts. Yes. We are only halfway there yet. And that's another reason why superposition is not as preferred if you have more than, let's say, 3 sources. I would, more than 2 or 3 sources, it becomes highly inefficient and time consuming because it adds up. Yeah. Yeah. All we're doing is you're breaking it up. So we are not looking at anything else. Yeah. It's like a light prism. You pass light to a prism, splits into different colors. You put another prism in front of it, converts it back into white light. And that's what we're doing. We're splitting it up into multiple circuits, we calculate, and then we again add them all up. So if I say, let's say if this is R1 and I wanted to find VR1, let's say I wanted to find VR1, I would perform my analysis for the entire circuit and I would find VR1. Okay, but this will be VR1 only due to VS1. I would have to analyze the circuit a second time, and I would say this time only IS1 is active. So if IS1 is active, VS1 is reduced to 0, meaning it is a short circuit. You have resistor R1 and the other resistors. Current source IS1. And of course, VS2 is still 0. So now you analyze the circuit second time and you find VR1 again. And this VR1 is due to IS1. So I'm just changing the notation. So here it was VR1 due to VS1. Here it is VR1 due to IS1, the second source. You analyze the circuit a second time. The circuit changes because REQ is different, right? REQ is different because now we're looking into the circuit from the perspective of the current source. So you have to reduce the network of resistance again. It's a different circuit. I want to emphasize this again because you will use this concept again and again. When you find REQ for the first one, it is from the perspective of VS1. And so this resistance is different than the resistance that you would get from here, IS1. Okay, so you have to perform a completely new analysis. You again repeat your analysis. Analysis steps actually. And then now if you have VS2 active, well, VS2 is on the right here. And then everything else is reduced to 0. So this is 0 short circuit. Current source is now open, and you analyze the circuit a third time. And you find VR1 due to VS2. So this is a third analysis for the third source. That's stupid. All right, let's see. And my actual VR1 is now equal to VR1 due to VS1 plus VR1 due to IS1 plus VR1 due to VS2. And that is for only one single resistor voltage. Imagine if you'd had to find all of the resistor voltages and all of the resistor currents. How many resistors do we have? 1, 2, 3, 4, 5, 6, 7. That's 7 times 3, 21, plus the occurrence 21. So 42 quantities. You would have to find 42 quantities. Does that make sense? And so superposition as the analysis technique is straightforward. It's easy. However, it is highly inefficient. The more number of sources you have, the longer it is going to take to solve for the quantities. If you just need to find like 1 or 2 quantities, that is fine. But if you need to find all of them, or at least more than 10, then it just multiplies the number of sources. If you have now 5 sources or 6 sources, it's gonna take like half a day to get everything done. And so again, superposition is a straightforward technique, extension of the previous one. All we're doing is building step by step, on the previous techniques that we learned. Any questions? Yes. Yes. Yep. So it's a good question. You would assume a polarity at the beginning of the analysis. So the question being asked is, do we have to worry about the polarity? Yes, so we do. So we would mark or assume the polarity of a voltage and the direction of the current in the original circuit. And then you solve for the rest of the circuits, like all of your analysis techniques, keeping that polarity in mind. So if your answer turns out to be negative for one of these quantities, you still simply add them up, but then you take the negative sign into account. And luckily, well, it's not luckily, but the example that I have actually does include this exact same scenario. So let's take a look at that example. Still have about 6-7 minutes left. But any questions about the procedure, about the theory behind this principle? Okay, so question being asked is determine the current I2 using superposition principle. I2 is already given to us right here. It is flowing from the top through resistor R3. Okay, resistor R3. Circuit has 2 sources. Vs is 10 volts. Is is 2 amps. Resistor R1 is 5 ohms. R2 is 2 ohms, and R3 is 4 ohms. Okay. Now, if you take a look at R2 and R3, we can see that they are in series, right? So right off the bat, the absolute first step I will do is I will combine R2 and R3 into one single resistance. Okay, just to keep things simple, or actually make it simpler. So as a first step, what I'm going to do is I'm going to combine R2 and R3 into a resistor, and I'm going to call it R4. I mean, we can call it anything we want. It doesn't really matter. And I2 is still coming down here. R4 is simply R2 plus R3. And so that should give me 6 ohms. This is 5. So 2 sources, and I just have one quantity to find. That means I need to analyze only twice, or once for each of these quantities, right? So I'm going to say when Vs is active, the quantity is going to be noted as I2 Vs. All right. So Vs is active, current source is 0, meaning it's removed from the circuit. All I have left is 2 resistors. The circuit changes every time, and that's why it's very important to actually redraw the circuit every single time. And I2 due to Vs is right here. Because the current source is removed, the node between 5 and 6 ohm resistance does not have a third connection, and so they are in series. I can combine those series resistances into one, which is 11 ohms, and simply apply Ohm's law. So I2 Vs is 10 divided by 11, comes out to 0.909 amps. 909. As simple as that. Now, when I say as simple as that, I do not mean like all circuits are like this. Just this particular circuit, as an example, it's straightforward. Note, at this point, depending on what kind of circuit we have, you can apply anything you want. You can apply Ohm's law, you can apply KVL, KCL, voltage division, current division, which is actually what we're going to do for this next step. Any questions? Any questions at all? So again, remember to redraw the circuit, because the circuit always changes, right? When you remove a component or you add a component, circuit's always going to change. So the analysis that you perform is going to change. Now, if I have IS active, went too far. Oh, IS active, I'm going to call I2 as I2 subscript IS. Now my voltage source is a short. I have a current source that is flowing down, and I have a resistor right there. 6 ohms, 5 ohms, and 2 amps. All right, take 10 seconds, look at the circuit. Tell me what you see. Yes. Which ones? Well, for series connections, we need 2 components to share a node, and only 2 components at that node, not more than 2. So if we take a look at the circuit, it's obvious 2 and 6 are in parallel because they share a node at the top, node at the bottom. But because the voltage sources are short, what happens is this 5 ohm resistance is connected at this node. It's only sharing one node. But because of the short of the voltage source, the 5 ohm is now connected to the 2 amp source also. And so they share, all 3 of them share this node, and all 3 of them share this bottom node also. And hence all 3 of them are in parallel, and I can redraw the circuit like this. Does that make sense? So you have a 2 amp current source, 6 ohm resistor, 5 ohm resistance, and they're in parallel. The 2 amp current source comes down here. It's going to split in two. One of them is going to the I6 ohms, the other one's going to the 5 ohms. So what technique comes to mind? KCL, you can apply KCL, absolutely. For KCL, we need to calculate, well, we don't have the other two currents, right? So it's 3 currents, so it's 2 amps being divided between the left and the right branch. So we can apply KCL, but then we need 2 quantities to solve for the third. So it's current being divided. Current division. Yep, one step answer, current division. So for current division, let me mark the original polarity for I2S. And we can apply current division. REQ here is going to be 5 times 6, which is 30, divided by 11. I'm not sure if I remember how much 30 divided by 11 is. It's going to be 2.727. And then I6 ohms is going to be 2 amps times REQ, which is 2.727 divided by 6. And this comes out to be 0.909 amps. But wait, we are not yet done. We have to sum them up, right? Because we divided into 2 parts. And this goes back to the point that was asked a few minutes earlier. The polarity of that current, the direction of the current is coming from the top. The 6 ohm resistor current that we just found is actually going up, not down. So it's the actual opposite polarity. And so I2 due to IS is equal to minus the resistor current. And my total IS or total I2 is the sum of both the currents. Zero. Okay, we'll end class here. Superposition homework is considered assigned. If you have any questions, I have office hours today. Again, we are on the Monday schedule, so I have office hours. In any case, I will be available in person via Zoom. I also have a few minutes before the next class. If anyone has any questions, I am available. I received your email and I'll forward it to the grade. Yeah.
Ours due tomorrow. I just want to make sure I'm not like doing the same mistake.
Which one?
The free lunch due tomorrow, right?
No. Yes, Wednesday.
Yeah, I just want to make sure I'm not doing